All right, welcome back. We're going to go into our second part of section 7.3. And this is really the learning target is around our central limit theorem. But to demonstrate this, we're going to say who has better ACT scores, Stony Point or Cedar Ridge. And remember, ACTs are scored from 0 to 36, and they're always whole numbers. And we're going to use an applet. Now, if you want to go ahead and go into this, here is the link to it. And there's an underscore right here and an underscore right here. But go ahead and pull that up. I think that will help you visually see what's going on here. Okay. And if we click begin, like it says, we get to see a population distribution. And it's approximately normal. It looks like the mean is at 16 and the standard deviation is 5. And I'm not guessing at these. The left-hand side of the applet tells you those values. So now we're going to click animate, and it's going to take a sample of 5 ACT scores. These were the 5 scores I got when I did it the first time. I then calculated the mean, so that's the value of the blue box on the applet. And it's the symbol I use is X bar because this is the mean from a sample. I then clicked animate several more times, and I changed it to 10,000 instead of 5. So it's going to take 10,000 samples that each sample is 5 test scores. And again, look at the stats on the left-hand side then. And the blue boxes have created a sampling distribution of X bar. So the way we know that the sampling distribution is approximately normal is if the population is approximately normal, then the sampling distribution is approximately normal. Okay, so that was from last lesson. So now we're going to take a look at Cedar Ridge's scores. And to see these, if you clear the lower 3, change the distribution using the drop-down menu from normal to skewed. And now let's look at this distribution. It's skewed to the right. And what that means is that most students do poorly. Only a few students do very well, the side where the tail is. And if I change a few more things on my applet, so change both of the bottom 2 drop-down menus to mean, the first one I'm going to change to n equals 2, so that means the sample sizes are 2. The second one I'm going to have a sample size of 25. So what I'm wanting you to do is compare the distributions based on sample size. So we're comparing a sampling distribution of 2 versus a sampling distribution of sample size 25. And if we were to describe the shape of the sampling distribution when our sample size is 2, it's still skewed to the right, but not as strong a skew as we had in the population. However, the sampling distribution when our sample size is 25 is approximately normal. And this is our central limit theorem, that when our sample size is large enough, and we define large enough as greater than or equal to 30, then the sampling distribution is approximately normal, even if the population was skewed. Okay? So this is a real key part of statistics, is that even if your population is skewed, when you use a large enough sample size, which we define as 30, greater than or equal to 30, then your sampling distribution will be approximately normal, which will allow us to use our probabilities. So again, that's the central limit theorem. And the key learnings here is our central limit theorem. CLT is how you'll see that abbreviated. And it simply states what I just said. The sampling distribution of X bar, so when we're talking about means, it's approximately normal if the sample size is large enough. And the sampling distribution looks like this, that our mean value for our sampling distribution is the same as the mean of the population. The standard deviation of our sampling distribution is the standard deviation of the population divided by square root of n. Again, don't forget that square root. And once we have this, we can then calculate z and then use table A to find our values. And again, here, there's the check your understanding. I highly encourage you to do this on your own and then come back and check your answers. So pause this, try the problems. Okay, welcome back, and let's quickly run through the answers here. The sampling distribution is going to be approximately normal because the sample size was large enough. 100 is greater than or equal to 30. So based on the central limit theorem, it is approximately normal. We do need to check the 10% condition, which allows us to state that the mean of the sampling distribution is the same as the population. And the 10% condition says that if our sample is less than or equal to 10% of the population, we can make these assumptions. And certainly 100 is less than 1/10 of all the iPhone users out there, because there are millions of them. So we calculate the mean for my sampling distribution and the standard deviation of the sampling distribution. We get 0.375 hours. If I want to calculate the probability of the weekly screen time for my sample is between 12 and 13, I'm going to have to calculate two different z-scores, find those probabilities, and then subtract them. So the z-score for the x bar being 12, I calculate, I get -4 as a z-score. -4 is not on my table, so I'm going to have to use the calculator to find the probability of getting a z-score of -4. And the command on here is I'm going to go into my distribution menu and choose normal CDF. Put in the different values, and I get a value of 0.0003. So tiny, tiny thing. I then calculate the z-score when x bar was 13, put in my values, and I get a z-score of -1.33. Using the table, here is the probability. That should not be an equals. That should say like an arrow. And then I have to subtract the two to get the area between them to represent the probability. So 0.0918 minus 0.0003 is still approximately 0.0918. And again, that is your central limit theorem, which allows us to say that if our sample size is large enough, so greater than or equal to 30, then our population for our sampling distribution is approximately normal. Okay, one more video to cover this section.